get ready. So we'll find out if Professor Baddick usually operates that way. They usually go right to the end, and I think we've had a class with him in the past. And so anyway, we'll see how it goes over time. So today we're going to talk about the one sample T procedures, both hypothesis tests, the confidence intervals, and how they relate. And in this first chapter, 1 and 2, there's these procedures are simpler in the sense that it's just comparing one group or comparison of groups, two groups, and as the course develops, we will have more involved procedures and deal with more complicated data structures, more complicated hypotheses. But we use these particularly to get going. It helps introduce the software and the computing to be able to do things with these scenarios. And on Friday we're going to talk about robustness. So what assumptions do we make in some of these procedures? How would we examine them, whether they're true or not? And then how important are they? Why do we really care about assumptions and how they impact our different procedures? On Monday, we would do a little bit more look at transformations. And one thing that we do want to get going is having the small presentations on an element of class material. Right? And so on these 2 days, or maybe looking to Monday, would be a little bit more time for preparation. One, potential topic, would be to look at the impact of a transformation on a data set, right? So there are different data sets in R that I'm aware have some issues in terms of being very skew, or very, some things. If any of you have used data in other classes or other research topics or anything like that, the idea would be to just talk about a data set. So here's a data set. This is what it looks like in a couple graphical presentation, histogram, simply plot, box plot, or something like that. And then if you transform it, take logs or square roots or do something else, what happens to it? So essentially it would be talking about one data set and the impact of a transformation or two, right? So that would fit in and give a chance of just presenting some data, and maybe you have some data that you've used in the past, but I would have some suggestions as well. So this one would be Monday. I'm going to be away tomorrow for some business, but I'll be on campus on Friday for regular office hours. So if you want to go first in this, then we could talk on Friday, talk about some things, and again, it would not be necessarily too long, but a chance to involve you more in the discussion and things like that. And if I don't get volunteers, I'll probably start picking people to assign, right? Maybe randomize names and start going through a list of names, just so that we get the ball rolling, and then everybody can do that. So you don't have to tell me right now, but if you think that this would be good, then for you to do, then yeah, we'll come back to that. So we're going to talk about these one sample T procedures in here. So the idea here is there's one sample from a population. So we have some data values, y1, y2, y3, up to y sub n. And we'll erase it, get that out of there. And there's some population that these things are from. And if we're interested in the population mean or average, then a fairly logical choice for estimating the mean is just going to be the sample average. bar, just taking the write this down, going from 1 to n of the y sub i's over there as an estimate of that. Right. And we want to have a procedure for summarizing the information, about mu based on the sample. So our sample estimate, y bar, right? So it's going to be the what we're going to use as the estimate of it. You can talk about things as this being an estimator, right? In the sense of calling it a function, right? That this is a procedure. It's what we're going to calculate from the data once we get it. So this equation gives us a prescription for what we're going to do. And that sense, it's an estimator. Maybe it's an estimating function, and going to give an estimate for that. Once we get data and get numbers, then the y bar in the sample based on actual values, you call that the estimate value or estimated value, or simply the estimate. So in one sense, it's going to be what we calculate and a number, but it's also kind of a prescription for the procedure or formula. And every once in a while, it's good to distinguish between the actual value you get for something and then how you're going to go about it. What we really want to evaluate is, say we get a number of 5.6, we're not really, when we talk about the procedures and how things operate and how they perform, yeah, we want to know, is 5.6 really close to the average in that sample? But when we think about statistical procedures and these different methods that we're going to develop, we're interested in how they perform over many possible samples. So it's really, how does this work as our estimation procedure work as a prescription for doing things in terms of performance, right? So we can go to a little bit of theory in the population. Right? If it has a mean of sigma and a standard deviation, of sigma, let me just look at this. I can make it a little bit narrower. Let me see if that is a little bit better. Notation. Okay, we're just going to go on. And so we have this y bar under the population. So under the assumptions that, say, the yi's are independent observations from the population. Maybe you can think about them as random sampled, or at least not being tied together in pairs. Then we can say that the average of y bar is our population average. So on average, our estimator is going to give us the right thing, what we would like, and the standard deviation of y bar then is the sigma from this measurement of the individual values divided by the square root of n. And so, but that's not, sigma's not known, right? So we're going to estimate that. Is unknown. So we're going to estimate, so we estimate sigma by just the sample standard deviation S. So that one I'll write on the next page for space. Right, so the sample standard deviation, S is the sample standard deviation of the n values we have. Right? So S is, we're going to add over all of our cases the yi minus y bars squared, divide by n minus 1 on the sample size, and then take the square root of all of that, so we'll get that value. Now it turns out that these estimates from probability theory says that if you take our average and subtract the mean, since the average of this one in different repeated samples should be the population average, this should be 0 on average, right? And divide it by its estimate of the standard deviation. That this thing is called a t statistic. Right. It's called t, and under some assumptions about the data being roughly normal or normal, right? This thing, so if the y's and i's are normally distributed, right, then this thing has a certain t distribution with n minus 1 degrees of freedom. Distribution. Oops, it doesn't like writing down there. Sure. I can't do it. This extra stuff out of here. Okay. Now can I write? I go slowly. It has that t probability distribution. And so we can think about the probability, this probability distribution for t, right? And that t distribution is nice and symmetric about 0. This is the t n minus 1 probability distribution. And so this curve is some density curve for the t distribution. Put a little t here, so the little values of t. And so it has a certain height. This f of t is the probability density function. For the t n minus 1 distribution. So in a probability textbook or a textbook with more formulas, you can look up the functional form of that and evaluate it, evaluate t for the height. And we can do things like figure out kind of a central 95% of the distributions. What are the most common values of the distribution? They're near 0, plus or minus some amount. If you randomly got a sample and randomly got one value of t, it's going to be some value on the real line around 0. And approximately plus or minus 2 for most cases. It changes depending on the degrees of freedom. Small degrees of freedom are wider, large degrees of freedom are narrower, but it's going to be kind of plus or minus 2 approximately. So knowing this, right, we can then set up some hypotheses. Right? So hypothesis S. So we think about our population. Right? Has some value of mu, and our null, we're going to be asking the question, what is that population average? Okay. And the null hypothesis is going to be some standard value. Right? No change, the general population value. We're going to do this with a matched pairs study as a data example. And then the question is there any change at all? Right? So that would become 0. For the general case, you can say, so mu sub 0, right, is the null mean value. So there's that. The alternative can be that it's just not that. H of A is not equal to mu sub 0. So under the null hypothesis, right, when we did the permutations and the other hypotheses, we always look at the distribution of a statistic under the null hypothesis. So our test statistic that we use is this t-value, y bar minus mu s over the square root of n, all in the denominator. But under the null hypothesis, right, it's mu sub 0. So if we have the null hypothesis is 0, then that's just going to be a 0 there, and it's just going to have the value of y bar. Right? But if it's some other value, like we think that the average is supposed to be 100, or we have the population averages from the previous time period, and now we're doing a new sample under new conditions, it could be that average under the context. But then probability theory says that let's go back. Under the null hypothesis, so assuming H0 is true, assuming mu does in fact equal to mu sub 0, right? But this t statistic, right, our test statistic, has a t distribution with n minus 1 degrees of freedom. And so if we've got an unusual, how far is y bar from mu sub 0? Well, it's going to be measured in these standard error units, s over the square root, and how many of those are weighed. But we're going to ultimately judge it in comparison to this particular probability distribution. If it's out in the tails of that, if it's extreme, it's something that's not very likely to happen, right? So if we're going to get something out here much above 2 or much below -2, then the chance you're bigger than that, right, or less than something out here is pretty unusual. So just randomly picking from a t-distribution where the probabilities are expressed by, kind of the relative chances are expressed by the height of these curve, it's very small out here and very unlikely. The area is quite small. This is just like extraneous thing here. So based on that t-distribution, as this distribution, and based on this, we're going to compute a p-value. We're doing the evaluation, right? So on the next page, we'll write down the formula for computing that, the symbols for computing that. So we calculate a p-value. If it's two-sided test, we're going to be 2 times the probability that a t-distribution with n minus 1 degrees of freedom is greater than the absolute value of the t statistic. So if it's a positive value of the statistic, we calculate the probability that we're greater than or equal to that. And because it's two-sided, we double it for the p-values, right? So our picture here's the t at 0. And our p, say this is our t statistic value, right? So we're going to calculate this area up above that, and then double it. This curve is the t with n minus 1 degrees of freedom. Right? And so, right. The other picture, right? if our t statistic happened to be down here, call it just negative t to emphasize that it's negative, right? Another way of defining the tail area is we'd want this area out here. The t is symmetric. So if we take the absolute value and look at the area going up here, it would be the same as the area to the corresponding part here. But to write it concisely in just one little statement, taking the absolute value and doubling it, right? And if the p-values are small, if it's an unusual occurrence that we've seen, right? Our p-value is less than or equal to alpha for some chosen threshold value alpha, right, we're going to reject the null hypothesis. We're going to reject the A0 at a significance level alpha. So usually, in medical studies or things like that, when they're writing a protocol, they say we're going to do testing at 5% level. And we're either going to do one-sided or two-sided testing. So it's all pre-specified. And 5%, 0.05 is usual threshold. But in some studies where you really want to confirm things and it's very, very critical, 1% might get used if you're kind of exploring and searching around and kind of generating possible hypotheses and things for study later on. It might get relaxed, 0.10, something like that, 0.05 around there. It's very typical. Actually reporting the p-value itself is more meaningful, right? So just saying it's less than 0.05 doesn't tell me is it 0.001 or 0.02 or 0.045. And I'd rather have the p-value itself along with the y-bar and to know more about the actual results, right? And usually major findings in healthcare or agriculture or other phenomena in psychology and are not really decided with one study. And there's usually a number of studies that are related and similar but slightly different. And if more than one study can show things, it kind of confirms that yes, this is not just one of those times that we get just a rare, random, strange occurrence, right? Almost every study will have some limitations. There's only one subpopulation, a specific group. The treatment or the procedures were implemented a certain way, right? Certain dose, certain specific formulation of the drug, a certain laboratory making it, and it can show a benefit or an effect in that study. But then if somebody wants to go out and use it in the real world, they might have a different manufacturer, a slightly different dosing protocol, a slightly different population that it's being applied to. The population in the real world might have other complications, other medications that they're taking at the same time. So a follow-up study might try something on another one, and that would add together. That's not part of this formal procedure, but just the reality. If you communicate more information about your study and the details of who you're, what you're doing, along with the p-value, an exact p-value, then people can get more information out of it. But any questions on that one? So the other way is to turn this into a confidence interval, right? Instead of just saying, here's our y-bar, and we don't reject 0 or don't reject some value, we might be able to give more information, right? Let me go back over here, try the nice thin one. So confidence interval. Again, we're asking the question, what is the population average U? And we have our estimate or our estimator function. Okay. Is y bar, so we're going to get our data, we can report the sample average, but how should we think about that? How accurate is that? Do we really have sufficient evidence to say that mu is very close to that, or this thing is very close to mu? Or do you have to be a little bit more cautious? Right? So the logic for making a confidence interval, right, is we can say things about that's the letter alpha there. I'm going to make the tail look a little bit big. Let me just see something. Yeah, okay, good. It stayed that. 1 minus alpha confidence interval. For mu. With the thunder and lightning, I'm wondering when the power is going to go off and this is going to go. I'm going to save this right now. What's that? So that, so if it just goes out, then we don't lose that part. Right. So we can make a probability statement that's true. The probability that a t-distribution with n-1 degrees of freedom is between two values can be set up to be alpha. Right? Or 1 minus alpha rather. So if alpha is 0.05, then 1 minus alpha 100% is 95%. So like a 95% interval. So we would call this point the 97th percentile up here, and the n-1 0.025 percentile on the bottom. And so this is a value. These are two values from that particular distribution that cut off the 2.5% tails and leave 95% in the middle. And we can calculate those things in R. So that's a probability statement about the t-distribution that should be true. Right? We're going to work with the equations inside and put our t statistic that has that distribution in the middle. Right? So we have this t n-1 0.025 is less than, I'm using, this could be, I guess the general case would be alpha over 2. But let's just think about 5%. So y bar minus mu, right, s over the square root of n is here, and t n-1 0.975 here. The probability that you're between the t distribution, that this statistic, right, our test statistic there ends up between these two values is 95%. This is not under the null hypothesis, so this is the general value of mu, right? Whatever mu is, right? And so we can multiply through by s of the square root of n. You can think, if you want to think about this as one equation, you're multiplying both sides of that one. Or if you think about this as one equation, you're multiplying both sides of this one. But what you get is that t value, 0.025, s over the square root of n, is less than or equal to y bar minus mu, is less than or equal to the upper one, 0.975, right, s over the square root of n is in there. Right? And then we could add mu to all parts of it, and the equations are still the same. Right? If you want to think about it as this one, add mu here, and add mu here. Think about this as an equation, and add mu to this one, and add mu to this one, and the equality is still the same. So on this side, you end up with, well, we're going to, and then also subtract that thing. So what we can write, this side can become mu is less than or equal to y bar minus the t n-1 0.025 times s over the square root of n. And this side over here, this equation, add mu and subtract that other thing. So mu would be on the top side of this one. Right? Y bar minus, and subtracting this, there's t n-1, the 0.975 thing, s over the square root of n. Right? So we end up with two equations that have mu isolated. And we can put those back together. Right? So we can have mu is, this thing is less than mu, and then mu is less than that one. Right? And so we get equations then. I might make this a little nicer. I want people to write everything down. My handwriting's not great anyway. And then pen, I try. If things get too unclear, please let me know. So y bar, the lower one was y bar minus p n minus 1.975, and then s over the square root of n. And the other one was minus this t n minus 1, 0.025 place, and then s025, s over the square root of n. But this one, right, this t n minus 1, 0.025, because of the symmetry, right, of the t, right, if you're down in the lower tail below 0, it's the negative of the kind of corresponding point on the positive. That is n minus 1, the negative of the 0.9751. Right? And this 975 value is going to be up around 2. Right? So you make that switch, you get the usual form that, if you plug that in there, we report then a 95% confidence interval for mu as y bar plus or minus. So once you put that minus in there, it becomes plus on this side, right, of the t 0.975, right, times s over the square root of n, n minus 1 degrees of freedom for that thing, right? And then minus is on that side. So it's, it's written as plus minus, but it's really kind of minus on the left and then plus on the right. And you get this interval. So the idea is that we're 95%. It's not really a, yeah, so that's the interval. And then we get some of the interpretation. We don't really think of mu as random, right? We don't, in this context, we don't really think about mu as moving around. Right? We have our sample, and we're going to calculate this. This gives us two numbers, a lower end and an upper end. And we don't think about mu as bouncing around and maybe being in there, right? Mu we think of as fixed. We're taking a random sample, and our random sample is given this, and maybe our interval that's come from our random data collection has landed in a spot that covers the real value. And so with this type of interval, we say we're 95% confident. We are 95% confident that the interval contains the true mu. So often it's a little picture is drawn to illustrate that, the line being at mu, and then a bunch of different intervals, and most of them cover, right? But every once in a while there's some that just miss. Right? So if we have the real value of mu, we're going to get a value of y bar and put an interval about it, and we're successful because the interval actually covers mu. And says our best estimate is here. We think mu is actually here. We're off just a little bit, but fortunately our interval shows us a reasonable range right there. And other times you can be a little bit further away, right? Sometimes you'll be a little bit below the target, right? These don't have to be the same width because we're using the value of s. That will change as well. Every once in a while we'll get a value of y bar when combined with the interval. The width of the interval will just miss. So about 95%, 95 out of 100 approximately. And then 5 out of 100, right, on average, could miss. 2.5 out of 100, or 25 out of 1,000 would miss high, about 25 out of 1,000 would miss low. but it worked pretty well. Right? And if you want to miss less often, if you wanted 99% coverage, right? So that's 100, 1 minus 0.01%. So it's like a significant level of 1%, a stricter standard for your performance. You want less error, less missing. Right? It effectively comes up to, making these a little bit wider, right? And the ones that covered before should cover, and then a few more of these, if that's drawn right, if it's a little bit wider, a few more cover. There'll still be 1 out of 100 that misses typically. Right? Where exactly does that change get done? Well, the T.995 value is greater than the T.975 value. Right? So this is right. So half of 5% is the 2.5%, and then 1 minus 0.025 is the 0.975 cutoff. But if you want a cutoff that has more below it, that's further out, right, half of 1% is 0.5%, and 1 minus 0.005 is that 995 value, so it's further out. Right? So with 2 inference procedures, hypothesis and confidence intervals, they're both asking the same question, where's mu? Right? One says just generally, where is it? Show me the interval. And the other one says, is it this value? So there should be some correspondence, right? And there is, right? So confidence interval versus hypothesis test, right? If mu sub 0 is in the confidence interval, right, then H0 mu does not equals mu sub 0 is not rejected using a 2-sided alternative. So the confidence interval covers it, it's not going to be rejected. It's going to be, if it's in the confidence interval, it's close enough so that the t-statistic is smaller than the cutoff value, the critical value from that, right? But on the other hand, it works the other way too. If mu sub 0 is not in the confidence interval, right, then H0 mu equal mu sub 0 is going to be rejected at that corresponding significance level. And the counterpositive of these things also, are true. If you do not reject, right, then it's going to be covered by the confidence interval, and if you do reject, then it's not in the confidence interval, and so there's this 1-to-1 correspondence in this particular testing procedure. Right? So on Friday, we'll look at, these assumptions a little bit more and how do they affect these kind of statements, like 95% coverage and significance levels, and which ones are more sensitive and what can be done about them a little bit. Right? But any questions about? So we'll look at a numerical example. Right? So I have this file here, this second case study file. That's from chapter 2. So these were of twins, monozygotic twins, right? And they're in pairs, so there's 15 pairs of them, right? So they have the same genetics. But one of the twins at the time of the study was diagnosed with schizophrenia, right? And the other one was not. Right? So they have the same genetics, right? I don't know if we have enough details to know if they grew up together their entire lives, but they're probably exposed to a lot of the same environmental influences. And that's why studies on twins for things like this is, very valuable. They volunteered, and a measurement of their brain volume, hippocampus volume, which they could do through imaging, was measured in cubic centimeters, right? So a little kind of like a cubic centimeter is a little box, right? Not very big at all, right? It's 2.5 centimeters approximately per square inch. So 1 square centimeter, right, is less than a quarter cubic inch, so not very big. But so they're measuring part of the brain, and these are the unaffected sizes and the affected sizes, and they're paired because they're linked through the genetics, right? So if one individual just ended up being large in size in general, maybe they'd have a larger brain size just corresponding to body volume, and not necessarily, of course, right? There's some very big mammals and animals that have tiny brains, but these are humans, and so maybe there's that correspondence. At least there's controls for it. And if there's any male-female differences at all, any type of things, this is controlled because they'd be both male or both female within pairs. So it controls a number of things, right? You could, in Excel, take the differences here and do a little pre-processing if you want and read it in, but it can also be done in R. I had downloaded this R script to this R data, right? So one strategy to get things going, right, is once you have those things downloaded, is if you right-click at it, you can open with RStudio, right? And it will pop into RStudio and have that loaded. Then once RStudio is going, you can open this with, and it doesn't seem to have an automatic link here, but it does find RStudio. If you needed to look for more applications, you could probably find RStudio. And the thing that it will do then is it will load it into the same session of RStudio. So once you have those two things downloaded. So for instance, in the next homework, I've chosen the problems and just doing a little bit of the coding so that should go up for next week quite soon. It has a little bit from chapter 2, one problem from chapter 3 that we'll be able to talk about, material for that on Friday. If you download those things, you can read them in. Right? The R code, like this one that I provide, will show a little bit of the commands like reading this in, right? Like this case study. If you open the R data set that's provided, I've already read in the case study. So if you see it existing over here, right, you don't necessarily need to do this command again to make it happen, right? So that can kind of, but the command is there. That's the type of thing that you would do. You would look for it under the files. This one. Okay, hello. Let's get a little frozen here. All right, try it again. Okay. We were going to do that. Okay. Let's just start again. So maybe the thunder or the lightning or something going through the system kind of short-circuited that. So but now it's in there, right? And it's kind of loaded where I was before, which is nice. And the days are there. If I was on this, maybe that will work. Yeah, that worked to get it in here. If it said it couldn't find it, trying that, but you knew that was there, then you might look over here and set this as the working directory. So you're seeing the pictures of the files there, and you set the working directory, then it knows to look there. So anyway, it's there. Let's take, you could look at the differences. So for instance, we could make this big. We could compare the groups. There's a box plot. We can look at what is the outcome? Difference. Oh, right, there's unaffected. Case 0202. Unaffected. Case 0202. Affected. Let's see. So that does 1 and 2. So let's, there's a little trick data frame, right, that will make it unaffected. So data frame unaffected is that one, and affected is that one. Right? So this, the brain volumes for the unaffected are like this, and the brain volumes for the affected are like that. And that's an effective display of the results, but you know, it is matched pair, so you could display this for the purposes of that, but you wouldn't analyze it as two separate groups, right? Because there's actually a correlation. We can actually look at the data to see if it's there. It's a small data set, so it's all there. With a bigger data set, and you did there's this head command to look at the heading, the beginning part, and the tail to look at the end part. If that matched up to your records and ideas, that would be great. In large data files, people often put total rows or some type of summary in the bottom, like maybe they're counting the number of missing values or something at the bottom of a row, and then you don't want to analyze things with that extra entries in there. Right? But we can take the differences. Right? And this will create a new variable, right, on this. So in the environment, now I have 3 variables, affected, unaffected, and difference. Right? We can look at the differences. So say a box plot of SO202 difference. And right, that's great. There we go. Right. And you know, our focus is on 0, right? If the twins had the same volume of that particular brain, right, we'd be at 0. That AB line, you can put a horizontal line at 0, LTY, the line type, so you put a little dotted line there. That's, you know, more than 50%, more than 75% of the observations are above 0, right? So it's kind of looking like the unaffected group has larger volume, and the affected ones that are suffering from schizophrenia have a reduced volume. Maybe there's something, you know, biologically causing it or related to it somehow. You know, it's not necessarily saying that that's the cause, but it's saying that is something that is systematically different between these groups and could be related. Right? Stem and plot is another way of looking at that. Right? So the actual sorts of values. Okay, so 202 difference. Those are the values. So 0.0. Yeah, it's there's a right. The stem plot that comes out here doesn't look quite like the one in the book. The one in the book had some gaps, right? And so it looks like it's grouping things by 2s, right? So 0.1, 0.2 is stuffed in here. 0.2, 0.3 is stuffed into here. So for some reason, by default, you know, the program has ways that it decides to make those things, try and make them look pretty. It decided to do that. But I wanted to see if I can do that. So there's help files for many of these things, right? And there's this, the data goes in there, and there's a scale factor. And so this controls the plot length. And then it says, here is it, the length will cause the plot to be twice as long. So I just tried that. Right? And so this broke it out, and this looks like what it is in the book. Negative 1.9, negative 0.2, negative 1.0, and so on. Thinking about, you know, what is a 1 cubic centimeter difference, right? Well, what cubic centimeter is a small size, you know, over my entire body, or maybe even the entire head. That doesn't seem like a very big part, right? But in this particular brain portion, right, so we sort, say, the just unaffected ones, people, their total volume of this hippocampus part of the brain is, you know, 1 to 2 cubic centimeters. So having a small difference as a percentage of this organ is kind of sizable. I think there's a difference of 0.2 is maybe the average that we're going to see. So it is kind of, it's not moving them, they're not half the size, but it is a pretty substantial fraction smaller. Right. And so there's this t-test command. If there's only one column of data, it does this one sample procedure. And if we run that, we get these results. Right. So it tells you it's doing the one sample t-test. This case, the default is mu equals 0, right? And so this is getting a t statistic value of 3.23, degrees of freedom of 14, and a p-value here, right? So that degrees of 14, there were 30 individuals, but 15 pairs. We're looking at the 15 differences, right? The cutoff values for the t, qt, so there's a help file, help of qt. Right. There's the density for the t, the probability that you're less than or equal to a value for the t, and quantiles for t, or getting random values by t distribution. Right. So if you get a random, you do a histogram, say with RT, do 1,000 random values, it wants a degrees of freedom. With 14 in there. These are 1,000 random values from a certain t distribution, right? And our value that we got was 3.2. So this time we want a vertical line up and down there, 3.23, and let's make it red. Oops, red. Right. There. So just by random chance, out of 1,000, we would get a few t-values that's bigger than that, but not that many, right? So I didn't save those, so how many random t's, let's do 1,000 of them, 14, is greater than or equal to 3.23. Right? In one sample, I got 4 out of 1,000, so it's kind of unusual. The p-value calculation, so 4 out of 1,000, 0.004. If it's two-sided, we've doubled that. So if we're just using simulation, we'd get something like 0.008 based on this. This one tells us it's 0.006. Right? So this PT command is the probability we're less than or equal to the value. So if we put in the 3.2289 and degrees of freedom of 14, this help file tells us, right? We need, for the probability of t, we need a value, a quantile for a certain thing, and a degrees of freedom. Lower tail, so you could tell it false for lower dot tail equals false, and it would calculate the upper one. I usually don't think about doing that. This NCP is a non-centrality parameter, so under the alternative hypothesis, we're not going to be centered at 0. We're going to be centered at something else. So we don't necessarily have to use that to calculate it, but it's another option. That's it. We might use that here.
So this is the exact same as doing a 2-sample t-test for the difference in matched pairs?
So it's just going to be one. So within the command, if you gave it both the affected and the unaffected, and told it was paired, right? Then it will do the same test. Effectively, it will take differences for doing the significance. So we can look at that. Yep. Right. So the probability you're less than or equal to that is this one. 1 minus that is 0.003. But if we're doing a two-tailed, we take 2 times that tail area. So 0.006 is where that comes from. Right, so Hattie's question, right? Help t.test, right? And there's a few things, x and y. One of the options that's here, variance equals is with 2 samples, but paired equals false. So paired is an option. Right? And so these options that have names, the name that is given there is the default. So it assumes it's not paired, and assumes variances are not equal. So if you do run a procedure and want to change it, you got to change that there. Right? Sometimes these won't have any impact, like if we already have one column, there's no way it can be paired. Right? And there's only one variance because there's only one sample, so that doesn't play any role. You can change the confidence level, 0.95, you can make it 0.99, something like that. But yeah, so if we do t.test, and in case 0202, we give it the unaffected one. In case 0202, affected ones, and we say paired equals true. You can either do paired equals true or paired equals t, it'll figure it out. It reports the paired t-test, right? So effectively it's taking the differences, so the mean of the differences is that. The confidence interval is the same t-test, so you wouldn't necessarily have to take differences yourself to put that in there. Yeah.
So just to clarify, the difference between like a paired t-test and a two-sample t-test. Two-sample t-test, we're taking the average of one sample, the average of the other, and then we're subtracting those two averages to get a statistic. And for the paired, we're taking all the differences and then we're taking that average for our test.
Effectively, yes. Yeah. Okay. But a critical difference comes in what is the standard error of the difference, because with the paired, we'll get the same numerical value whether we take differences and then average, or take averages and then take the difference.
Right.
Numerically, that's going to be the same estimate, right? Our same estimate of 0.1986 is going to happen the same either way. But which standard error do we take, right? And so that gets into this. So we'll talk about that shortly, right? So, but anyway, this would be the 95% confidence interval. So we're 95% confident that the average difference in this brain volume, cubic brain volume, is between 0.067 and 0.331 cubic centimeters. Right? So even though it's a small sample, we have an interval. It's not too, it's kind of wide, but not too wide relative to the, and it's very informative because it doesn't include zero. Right? Our hypothesis that it was zero is not rejected. If you can get a different null hypothesis as well, right? If for some reason you thought there'd be a 3% change or a certain change, like you were doing infants versus the same people as adults, right? Was the growth in that part of the brain, and you would expect a non-zero growth, right? You could put the amount of growth you would expect in there as an alternative, right? And then it will subtract it in there. So, but why do we need to pay attention to this? Why does it do that, right? So, it gets to what is the standard error. And in 340, okay, just barely enough time, right? So, matched pairs. We take the difference, like yi equals xi2 minus xi1, and then we do the standard deviation of these y's over the square root of n. And if it was two independent samples, well, in this case, the two sample sizes are equal, and this is an x. Or we take the variance of the first one over n, or n1, and the variance of the second one over n, and take the square root. Right? And so we have two very different variance formulas for y bar equals x bar 2 minus x bar 1. This is our estimate in either case, but the very different variance formula for that. Right? And the independent samples, the x1 and x2 are not correlated. So the variance of y is going to be the variance of x2 plus the variance of x1. And these two variances add together in here, right? Or y bar. Bars in there, right? However, in this case, there's a correlation. And if these x1 and x2 are correlated with each other, then the variance in the matched pairs case is smaller. So, matched pairs. The variance of y bar is going to be the variance of x bar 1 plus the variance of x bar 2, right? Minus 2 times the covariance of x bar 1, x bar 2. In independent samples, this is 0. Right? But if it's a positive covariance, if the x2 values tend to go together, and this is very large, then the variance of the y bar can be quite a bit smaller. Right? And so that's important to take that into account. And the way you could look at that here in R, right, what's the correlation of the case O2, O2 unaffected, and then the corresponding O2, O2 affected. The correlation between these two is 0.63, right? So the variance of, say, well, anyway, the next thing to do, we're basically out of time, but you could calculate the variance of the x bars, right? So for instance, the variance of, we'll do some calculation of the differences, right? Is that the variance of the case O2, O2 unaffected plus variance of case O2 affected is much larger, right? It's 0.149, that's 0.056, because you have that big impact of the covariance, the correlation with the two making the differences much smaller. And that can be some of the power of taking differences versus the baseline and measuring change rather than raw values. You know, raw values for something can be on this enormous scale, right? But once you take differences, the amount of change can be quite a bit smaller in comparison. So yeah. So the data structure means that you really do need to use a particular variance formula to make it appropriate. So on Friday we'll talk about in kind of the 1 and 2 sample cases, you know, assumptions and that are there and how they affect things. So I'll start out asking you, you know, what are some assumptions of those things? So if you look through the book and think about what assumptions, you get the list of things that are there. So if you have this first homework, I'll just take that. In general, you can just kind of make a pile and hand it in at the beginning, or at the end works out fine.
It looks like it's not raining.
Thank you.
I probably just jinxed it. As it looks.
Right.
Are you welcome?